Hi, now after the last 3 videos on the power supply design, I've had a few people ask, how do you do the PWM or the pulse width modulation voltage control instead of the 10-turn pot? Well, it's a good question, so let's take a look at it. Now when it comes to controlling a power supply like this, you've got 3 main options. The first one is the 10-turn pot, which I've been talking about, but they're quite expensive. They're about $5 to $10 or even more each, depending on where you buy them from. The second one is to use a digital to analog converter. It puts out, you put a digital signal in from your microcontroller, it gives you a voltage output, exactly like the pot. But I don't know, you're going to pay $2 plus for a digital to analog converter. Not many microcontrollers have a DAC actually built in. So what you do is you use the third option, which is pulse width modulation, and it's effectively free. Most decent microcontrollers these days have a couple of PWM modules in them, pulse width modulator modules, and all you need, it's not quite free. You got to pay for a resistor and a capacitor, but gee, you know, they don't cost much at all. So let's take a look at these. And there's a 10-turn pot, and they're very, very nice. And if you just build in just a linear power supply or even a switch mode one, and there's no intelligent microcontroller control in there at all, then I highly recommend you just use a 10-turn pot. You can use regular pots, but then you've probably seen those power supplies that have coarse and fine adjustment. It's probably a dead giveaway that they're not using a high quality, expensive 10-turn pot, and they're dicky. Trust me, just the fine and coarse controls, they're hopeless. Get a decent 10-turn pot, but they're $5, $10+ each, and you need one for voltage and current. Wow, there's like $10 to $20 just for your supply right there. Doesn't include the knobs. And if you're going for digital control, then, well, you're going to use, instead of a pot, because you're still going to have a knob on the front panel unless you use switches, then you're going to use one of these rotary encoders, and they're pretty cheap. They're only about 50 cents each or something like that, under $1. And you just put a little cheap knob on the top, and then you've got complete control. That is more than 10 turns. That's infinite number of turns. So these rotary encoders are great. They're easy to encode in software, and you can use this to drive via your microcontroller either a digital to analog converter or a pulse width modulator. And the goal for all 3 of these things is exactly the same. You want a voltage output. If you've got a 0 to 10 volt supply, then you want 0 volts to 10 volts output to drive to actually control your voltage regulator. And these do exactly the same thing. You turn a knob, or these two here, you turn a knob, but a microcontroller generates the voltage. Now, in terms of the DAC, here, you know about digital to analog converters, or if you don't, look them up. I won't go into them here, but basically they're a dedicated device. You feed a digital signal in via, usually, you know, like a serial input these days, an SPI or an I2C interface, or if they're built into the micro, they could do that, and they give you a direct voltage out. You don't have to do anything else with it. They're magic. But a pulse width modulator is exactly the same as a DAC. It works. It works differently, but it gives you the same result. It gives you a voltage output, just like a DAC. And the resolutions are exactly the same as well. Because if you're working with a 10 or a 12-bit DAC, it's going to give you exactly the same voltage resolution as a 10 to 12-bit PWM. So let's take a look at how the PWM actually works. Now, you can get PWM hardware modules, dedicated hardware block inside your microcontroller that does all this for you independent of the software. The microcontroller software can be off doing whatever else it likes, and the PWM module in the micro will take care of generating the PWM waveform. And I highly recommend you use those if you have them available. But you can do it using just any generic I/O pin, and you can do it in software, because all it is a digital waveform with a varying duty cycle. Now, what we have here, what a PWM signal is in this case, is just it's a fixed frequency, say 10 kilohertz or something like that, might be a typical PWM frequency. So this waveform just repeats at a frequency of 10 kilohertz. Now, what changes though is the duty cycle, or what's called the on time, from 0 to 100%, or what amount of time in that period that waveform is high. And it can be anywhere from zero, of course, 0% would be it doesn't go high at all. It just stays low. Your output pin just stays forever low. And of course, you're going to get 0 volts output. It's just low. It's a DC signal. But let's say it goes high for X amount of time. Let's say it goes high for 10% of the time. Then 10% of the time it stays low for 90% of the time. What do you get out? Well, you don't get out anything. It's a digital signal. But if you pass it through a low pass filter, an RC filter, first order filter like this, you will actually magically, as long as you got the filter values right, magically convert this PWM signal into a DC voltage from 0 to 5 volts. Because let's say we've got a 5 volt microcontroller and that's what its output voltage is going to be, either 0 or 5 volts. Well, when you pass it through the RC filter like this, it averages out that duty cycle or on-time value to a direct linearly proportional voltage from 0 to 100%, or 0 to 5 volts. So if it's on 10% of the time and off 90% of the time, you will get out 1/10 of 5 volts, or half a volt out of your RC filter down here. Magic. So you can see why it is actually a DAC. It's a digital to analog converter. It works just like a DAC. You feed in a value. In this case, instead of outputting it into a digital to analog converter, you put the value that you put in from 0 to 100% gets converted into a duty cycle or on time from 0 to 100%, and it generates an output voltage proportional to the digital signal or the digital number that you put in. Now, resolution plays a big part in these digital to analog converters and pulse width modulator circuits. And I said before, they're exactly the same. The resolution of a DAC is the same as the resolution of a pulse width modulator. Now, based DAC. That's sometimes what it's called. It's a PWM based DAC, basically, because it is a digital to analog converter, except it uses the PWM technique. Now, the resolution, let's take a pretty meager, pretty low-end 8-bit resolution, and most really cheap budget low-end microcontrollers, you know, the 50-cent ones, might have these 8-bit PWM outputs like this. Now, of course, 8 bits represents there's 256 different levels. Now, that means that we can set this resolution in here in steps. There can be 256 different steps in there from 0 to 100%. So what does that mean? It means that 100% divided by 256, each step we can get a resolution of 0.39% of our maximum voltage, which is 5 volts. Or in this case, 5 volts divided by 256, 19.5 millivolt steps. And if you're designing a 5 volt power supply, for example, then you would, with an 8-bit resolution PWM module, you'd be able to adjust that in almost 20 millivolt steps. That's not too bad for a generic lab supply, but let's say you doubled that to 10 volts, you multiplied it by 2 and you want a 0 to 10 volt output DC supply. Then you've got it, then your steps would be 40 millivolts. You know, it's getting a bit crusty. You might want to up that to 10-bit resolution. If you have a look at 10-bit and 12-bit resolution PWM modules, in the same case of 5 volts output, then divided by 1024 because it's 10 bits, 4.8 millivolt, almost 5 millivolt steps. Not bad. 12-bit one, well, hey, we're getting serious now. 4,096 steps in 12 bits. So we're talking a resolution of 1.22 millivolt steps. Fantastic. Now here comes that tricky thing to do with the difference between resolution and accuracy, just like you get on multimeters and a whole bunch of other stuff. Yes, a 12-bit digital to analog converter, be it PWM based or other type of DAC based system, then you will get almost 1 millivolt, just over 1 millivolt resolution or steps from 0 to 5 volts. and you do actually get that. You can control that output. You can jump it up by 1.22 millivolts, bang, 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 or drop it down like that. You've got that fine control. But the absolute value or the absolute accuracy, well, if you feed in completely 100%, are you going to get exactly 5 volts out? Well, that depends on how you power your microcontroller here, because the good thing about modern microcontrollers is that they're all CMOS. They're CMOS output, so they use FET switching on the output. So that means that they can get incredibly close, ridiculously close, to their input voltage rail up here on their output switching. So if you're powering your PIC from precisely 5 volts, 5.00000 volts, then you can pretty much expect close to that absolute accuracy on the output of your PWM here. There's a, there might be a millivolt drop or something like that, but it's going to be very, very close, okay, with these FET outputs. Now, if you just power your PIC or AVR from like a 7805, they're only 5% accurate. So the output of your pulse width modulator here is going to be 5% accurate, absolute as well. And that's really not much good if you've got a precision bench power supply. Now, you can compensate for that in software or pots with further gain stages or something like that. You can actually calibrate it and tweak it, but yeah, that's a bit nasty. But so sometimes you might want to actually power your microcontroller instead of from a regular voltage regulator. You can actually power them from a voltage reference, one of those precision, 2.5 volt voltage references if your micro goes down that low, or a 3.3 volt voltage reference, or a 5 volt voltage reference. And you can get those in like 0.1% or something like that, 0.2% for $1 or so. So you can actually power your microcontroller from that, provided that your microcontroller and the other circuitry you're powering from it doesn't take more than its maximum allowable current. But you can actually do that. So when you're designing power supplies like this, don't be afraid to actually power your microcontroller from a precision voltage reference. It can work and it can be very handy. And in the previous videos, I actually used an LT1009 voltage reference in the build, but you can use LM336, and there's hundreds or thousands of other voltage references, and some of them might have 40, 50 milliamps output capability, and that's a decent amount of current for powering a microcontroller. But just be careful if you're driving loads like LEDs and stuff directly from the microcontroller, then that current's got to come from the micro power rail, which comes from the voltage reference. But as long as you don't exceed that, you can get excellent absolute output accuracy as well as resolution on a PWM. So as you saw, if we have 10% on, 90% off during our period here, then we're going to get this RC filter is going to average that value out to 0.5 volts. But it's not just going to be completely DC. There's going to be some noise on that. Okay, there's going to be noise superimposed on there depending upon the values you pick down here and how effective this filter is. So we really need to take a look at it in depth at the filter and what values you need to get rid of, say, a 10 kilohertz might be a very typical frequency. Let's take a look at what RC filter you need to get a decent low noise output from this, which then usually you want it lower than your resolution. So if your resolution is 12 bits, you don't want the noise to be any more than 1 bit resolution, or 1.22 millivolts. Now what we're going to take a look at is a filter simulation program here. I'm using Filter Lab. It's from Microchip. It's an old program. It does an okay job. There's another one from TI and from various other people. Linear Technology do one as well. And they're all pretty old, but they give you a good feel for how filters work. In this case, we've just got our simple RC filter here with the buffer, and that's called a single pole filter. And we can change the filter up here. That's this number 1 up here. So if we go to what's called a second pole filter, you've added some extra components, and a 3-pole filter and a 4-pole filter. This is called a Salon key configuration. There's different configurations you can do, but basically the order of the filter, the higher the order, the greater the attenuation of those higher frequencies. Now let's take a look. Let's go to the first order filter. Now I've set the filter to have a roll-off, a nominal roll-off, or a filter cut frequency of 1000 hertz. So you can see that here, it's 1 kilohertz. And what that means, you've seen that, probably seen that formula before. It's 1 over 2 pi RC, and that gives you the cutoff frequency of your filter. Now, that it's not a brick wall cutoff, okay? What we've got on the x-axis here is our frequency, okay? Now, this is a logarithmic scale, so it's in decades, so it doesn't go linearly from, say, 100 hertz to 1000 hertz. Here it goes, that's 100 hertz, that's 200, then 300, 4, 5, 6, 7, 8, 9, and then 1000 hertz like that. Now, the reason we use a log scale like this is because it actually gives us a linear slope like this. It converts our logarithmic response into a linear slope, which will become, it's just easier to do, and it's easier to fit wide frequency spans into the one graph like this. So that's why we're using a decade logarithmic response on the x-axis. Now the y-axis here is the magnitude in dB. So right down here at 100 hertz, it's got 0 dB attenuation. That's the attenuation of the filter. So you feed in your signal, and what you get out, you at 100 hertz, you feed in exactly what you get out. There's 0 dB attenuation. Now, the filter cut frequency, that formula, 1 over 2 pi RC, that gives you your what's called minus 3 dB cutoff frequency of that filter. So as you can see, in that filter there, I've got it on the y-axis there, it's about minus 3 dB, and it's spot on 1000 hertz on the x-axis, because that's what we've designed it for. And then it rolls off after that. Now, you remember we've been talking about filtering out a 10 kilohertz frequency. Well, let's go down to 10 kilohertz. Here it is. How much is that filter attenuating our 10 kilohertz signal by? Well, if you take that over to the to the y-axis over there, it's minus 20 dB. And if you know your dBs, a minus 20 dB drop in amplitude is 1/10, or an order of magnitude. So if we're feeding in 1 volt, we're going to get out 0.1 volts. Now, the thing about dBs is that once you step down to, if you go down to, so in multiples of 20, that's an order of magnitude drop. So minus 20 dB is 1/10, minus 40 dB is 1/100th, minus 60 dB is 1/1000th, and minus 80 dB is 1/10,000th of your input voltage. Now, if we increase our number of poles, or the sharpness of our filter, you'll see that it gets steeper and steeper as we go off. Now the roll-off, which is specified in dBs per decade, can be specified in other things too, but in this case it would be dB per decade, and it gets just sharper and sharper. And as you can see, if we used a 5-pole filter, our 10 kilohertz signal would be attenuated by minus 100 dB. That is absolutely phenomenal, okay? But if we use our first order filter, which we've got, our RC filter, it's only attenuated by 1/10. So we're not going to filter out if we set our cutoff at 1000 hertz. So if you're trying to filter out a 10 kilohertz frequency PWM signal with a 1 kilohertz filter, it's going to do a pretty darn poor job of it. It's only going to attenuate that 10 kilohertz signal by one, or the 10 kilohertz ripple by 1/10. It's hopeless. It's 10%. Unbelievably hopeless. Now, what I've done here is to set the filter to 10 hertz. So there's the minus 3 dB cutoff frequency at 10 hertz, and you'll notice that at 100 hertz it's 20 dB down, and at 1 kilohertz there it's 40 dB down. So if you measure the difference actually between the 100, once it gets on this linear part of the curve here, if you measure the difference between the 100 hertz frequency at minus 20 dB and the 1000 hertz frequency at minus 40 dB, that's what's called 20 dB per decade. So that filter rolls off at 20, you get 20 dB attenuation per decade in frequency. So if we extended that graph out even further there, to 10 kilohertz, we'd find that it'd be down to minus 60 dB. So if we set our filter at 10 hertz, at 10 kilohertz, we'll have minus 60 dB attenuation of that 10 kilohertz fundamental frequency. And remember when I said it drops an order of magnitude or 10 times per 20 dB, then at 10 kilohertz, we'd be at minus 60 dB. Sorry, it's off the graph. I haven't got enough decades to show it here, but it's minus 60 dB at 10 kilohertz. So that's 1/1000th. That's the attenuation. So you feed in 1 volt, then you're only going to get 1 millivolt out. Now, just to be clear, that 1 millivolt I'm talking about there, and these levels I'm talking about, they only apply to a sine wave at 10 kilohertz. So basically all this filter talk we've been talking about doesn't actually apply directly those amplitudes to the PWM. It gets more complicated when you start talking a PWM signal, and in practice it's actually going to be lower than that. But let's use a ballpark. Let's say you did actually get 1 millivolt of ripple out. Assuming it transferred to your output through the regulator, then, and there wasn't any extra further filtering, then that might be okay. But generally you'd want to shoot for better than that. But with a filter cutoff of 10 hertz, that means you're not going to be able to change your output voltage really quickly. And on a DC power supply, if you're manually turning a knob, it's not a problem. You can't turn that knob very quickly at all. You're going to turn it only, effectively, 5 or 10 hertz at most, or something like that. Okay, you're not going to get huge, big step changes on your power supply because it's filtered out. All right, now we're actually going to do some real circuit simulation here with a PWM signal and with our LC, one-pole LC filter, and see what we actually get out. Now, I've set up this voltage. It looks like a voltage source, but it's actually a pulse source. I'm using LT Spice here, which is a free circuit simulation tool. I highly recommend you get it. It's pretty darn good. And basically what I've set here is I set the pulse width modulation voltage level from to 1 volt. So it's going to switch between 0 and 1 volt. Now, it won't do that if you're using a microcontroller that's, say, a 3.3 volt voltage rail. You will get 3.3, but we'll set it to 1 here just to make our math nice and easy today. Now, the period down here I've set to 100 microseconds, and that's equivalent to 10 kilohertz. So we're going to get a 10 kilohertz repetition rate on our PWM signal. And then I can set my on time. I've set it to 1/10 of that. So I'm setting it to 10% on time, or 10% duty cycle. It's 10 microseconds out of that 100 microseconds total. Okay, so what I'm doing is I'm going to go into the simulation command here. We're doing transient analysis, and I've set my stop time to 1 millisecond, and I've set my time step so it effectively samples or simulates a circuit every 0.1 microseconds. And if we hit that, and we run it up here, bang, there we go. And I told it, so we're only going to get, it stops once it got to that 1 millisecond period. And what we're doing is we're measuring this point here. You can see the little red probe down there on the circuit, and we're probing that point right there, which is the PWM input. And as you can see, it is 10%. And you can go in there and actually measure that precisely, but trust me, it's going to be 10%. So our on time is 10%. So we expect, if we're feeding in 1 volt here, 1 volt peak to peak, there it is, over on the y-axis here, from 0 to 1 volt, PWM signal, we expect 10% on time, we expect 1/10 voltage on here. Do we get it? Well, not quite, and we'll see why. Now the reason is that is actually slowly ramping up because there's an RC time constant. We started the simulation from 0, so we're going to have to go in here and we're going to have to extend that time period. Let's say set it to 100 milliseconds like that. Let's leave it at 0.1. It could take a bit of a while to simulate that, but let's try that again, shall we? Now it's going to be hard to see that if we zoom in, so let's click on the circuit here, bang, look at this. And you can actually see that window there, let's zoom to fit, okay? And bingo, you can see it rise up like that. That's our RC time constant that it takes when you first switch on the supply or change the voltage or whatever. It doesn't respond instantly, but it eventually settles down to, bingo, what does it settle down to? Go across here, exactly 100 millivolts average. Trust me, if you drew a line straight through there, it'd go right through the average point of that waveform. So there's our 1/10th. It's worked. Our 10% duty cycle has translated to 1/10 of that, or 100 millivolts output voltage. And if you look at the output on the op amp over here, you can see that that takes a little bit of time, but it responds to the same value. But there's a little bit of an offset there. That's going to be due to the offset voltage. But anyway, what we really care about here is this noise. Look at the ripple. You can see that the switch in frequency, because the RC filter we're using is not low enough in value to filter out all that noise. Who wants a power supply when you're trying to output 100 millivolts? It's got, what's it got? 10 millivolts of ripple on that. Hopeless. And that's with a filter frequency down here of 159 hertz, because if you do the math, use that formula, 1/2 pi RC, that's the 3 dB cutoff point of that filter is 159 hertz, and we're trying to filter out 10 kilohertz. So as you can see, it's not terribly effective at all. But let's try that again. If we actually change that to 1 microfarad, you'll find that this ripple here will decrease. We're increasing the capacitance by a factor of 10, so our filter frequency will go from 159 hertz to 15.9 hertz, and you'll find that because this is all order of magnitude, the ripple will also drop by an order of magnitude. So let's resimulate that. So it's about 10 millivolts at the moment. Let's resimulate that, and bang, it's slowly ramping up. It's ramping up, but as you can see, it's taking longer. It's taking much longer to actually get up to frequency there, because we've changed the RC time constant. So you can see that's taken 54 milliseconds before it even, 50 odd milliseconds before it even sort of starts to level out like that. And that's not too bad, actually. Now let's go in there and have a look at the ripple. We'll zoom right into this window here, and bingo, you can see it. There it is. That's only about what's that? Half a millivolt even. It's only half a millivolt ripple. Fantastic. So as you saw there was really quite a trade-off between the response time and the filter effectiveness, or the filter attenuation. Now, to do that, to get around that, we can add a second stage RC filter like we've done here, exactly the same. So we've gone back to our original 10K and 100N here, so that's 159 hertz nominal 3 dB cutoff, but we've added another identical one here, 10K and 100N, and we could do it with the op amp and use various configurations like a Salon key configuration and all that sort of stuff. But let's just keep it simple and put two RC filters in series like this, and if you run it, this is what you get. The green line there is the value on here, like exactly what we saw before. Okay, that's got our 10 millivolts of ripple on it. It's huge. But our second one here, after that, that is the blue line there. And check it out. That is, let's put both on there. And as you can see, it's beautiful. And if we zoom in on that, let's zoom in on that part of it there. Look at that. The blue one, smooth as a baby's butt. There's hardly any ripple on that at all. We're talking 0.1 millivolts, 0.2 millivolts or something. It's tiny. So that's just an easy way that you can get extra filtering on your PWM. Just add a second RC filter stage. I mean, sure, you can up these values here, okay? These 10K, this 10K and 100N, you can up those, but then your response time gets low. So it's better to add this second stage here, and then you can keep your response time fairly quick at 10 milliseconds or something like that. But it has much greater attenuation. So, we're down in the hundreds of microvolts there now just by having a simple 10K and 100N like that, a two-stage RC filter. Beautiful. Now, what happens if your PWM signal is, say, 5 volts out? Now, let's change it back to 5 volts here. But let's say because you've got a 5 volt rail on your microcontroller, but you don't want to get 0 to 5 volts out. You only want 0 to 1 volt or something like that. Well, what can you do? It's easy. You can add a resistor in here to actually attenuate that. So let's add that in and see what we get. So let's run it again with that. We've got our 5 volt signal here. Okay, there's our 0 to 5 volt PWM signal at 10%. So what do we expect out? We expect half a volt, 500 millivolts here. That was before we added this 10K though. So now we expect to halve that again, or 0.25 volts, 250 millivolts. Let's see if we get it. Bingo, we do. There's our 250 millivolts, but it's got the ripple. But if we look on the output here, then bang, there it is. Our blue line, our blue trace there, that's 250 millivolts. So let's run it again with that. We've got our 5 volt signal here. Okay, there's our 0 to 5 volt PWM signal at 10%. So what do we expect out? We expect half a volt, 500 millivolts here. That was before we added this 10K though. So now we expect to halve that again, or 0.25 volts, 250 millivolts. Let's see if we get it. Bingo, we do. There's our 250 millivolts, but it's got the ripple. But if we look on the output here, then bang, there it is. Our blue line, our blue trace there, that's 250 millivolts. Now here's an interesting thing I just wanted to show you quickly. We've got an LT1014 op amp here. I just chose this generically just so we could get something working from the library. Now, it just so happens that this is a fairly, good precision op amp. It's only got a couple hundred microvolts offset voltage, and you pay a bit of coin for this thing. So you'd expect it to work out quite well at low values. So let's actually try that. Now, I've changed my PWM here to 0.1 microseconds compared to the 100 microseconds period. So that's 1/1000th of our 5 volts maximum PWM voltage there. So if we're getting 5 volts here with 1/1000th on time, we expect 5 millivolts out of our filter. And if we run it, bingo, that's exactly what we get. There's our 5 millivolts, and that's the input to the, that's the first stage of filter, second stage filter input to the op amp, 5 millivolts. Well, let's also add on the output of the op amp. Wah, look at that, 35 millivolts. What's going on? Well, it turns out that this, if you look at the data sheet for the LT1014, it turns out that you can't actually go down to 0 volts unless you have a decent load on there. It's not a rail-to-rail op amp. So just be careful if you're actually, when you're choosing an op amp like this in this grounded configuration and you don't have a negative supply voltage for that op amp, just make sure that it's actually capable of 0 volts on its output. Otherwise, if we use this fairly high precision op amp, we'd get a 35 millivolt output offset. Terrible. So you might think that the solution to this PWM thing and the trade-off versus the response time versus the attenuation and the ripple and all that sort of stuff is to just up the frequency of your PWM signal. Well, yeah, in theory, that's great. The higher the PWM frequency you use, the easier it is to filter out with better response time. But the microcontroller is going to have a limit to how high a PWM frequency it can go based on the resolution. And generally, you can change the resolution of these things. You might be able to use a 10-bit resolution PWM, you might be able to use it as an 8-bit one or as a 10-bit one, for example. And it's going to have a maximum upper frequency. You have to read the data sheets very carefully to get that sort of info. But generally, you want to run them as fast as possible. Alright, enough of the simulation stuff. Let's actually feed it into our circuit, a PWM signal, to replace the pot which we used before in the previous videos. That's exactly what I've done. I'm using the function generator output of my Agilent scope here to actually replace the pot, and I'm feeding it in via a single RC filter, which is what we've looked at. And this is what I've got here. Instead of the voltage control pot, we've disconnected that and we're taking it down to a 10K and 100N low pass filter, just as we looked at. And the frequency I've got set, as you can see here. If you go in here, you can see I've got 100 kilohertz frequency, and our amplitude is 3.3 volts. So we're simulating a microcontroller generating that PWM signal with a 3.3 volt rail, the offset voltage, because this is a function gen that's got to be halfway in between, and we've got a 50% duty cycle or 50% on time. So if we're feeding in 3.3 volts, and by the way, I've also changed this feedback resistor here just to make the math easy, changed it to 10K, so we'll have a gain of ×2 in this amplifier control loop here. So if we're feeding in 3.3 volts that we've got here, we should get some ripple out of here, of course, because it's not that great, this filter on its own, and at 50% duty cycle, we'd expect to get 1.65 volts out of here, multiplied by 2, we expect to get our 3.3 volts out of here. Exactly what, and let's actually see if we get it. Well, if you have a look here, let's zoom out, there it is, there's our output voltage. It's pretty close, there's going to be some error in here, this isn't perfect, but if it was, you use more precision function gen and stuff, you'd get exactly 3.3. So we're getting out exactly what we expect. And this, the green signal here, which I'm triggering off, there's our 3.3 volt, 10 kilohertz PWM signal, and the yellow trace here is the AC coupled output on that RC filter there. So on the RC filter right there, that's our yellow waveform there. As you can see, that yellow waveform, 100 millivolts per division. We're getting 100 millivolts ripple on there. And let's probe the output and see what we get. And this is our output. I've just in the output of our power supply, our 3.3 volt output. And as you can see, it's there's not much on there at all, where it's still at 100 millivolts per division. But if we turn that up, you can actually see the ripple on there now, down at 10 millivolts per division. We're getting about 5 millivolts, 8 millivolts worth of ripple or something like that. And look at these little high frequency stuff in here like that. Bit of ringing there. That's probably due to our probing and stuff like that. But you really want to get rid of this sort of stuff. So that's not adequate ripple. If we just used that 159 hertz filter there, that's really no good at all. I don't like that one bit. Now you're probably asking, why did that output ripple drop from 100 millivolts to under 10 millivolts? It shouldn't have all just, if we were getting that here, shouldn't have all just passed through that straight to the output? Well, no, not really. Remember these caps we've got here? They're going to do some filtering as well. And that's what you get if you replace the 22 microfarad cap here down to 100N. Bingo. And it turns out that I still had 47 microfarad of capacitance on the output there. So I took that off, and what do you get? Magic. Look at that. Wham! That's an absolute shocker. And bingo, it's back to 100 millivolts. There you go. So it's actually now made its way all the way through. So all of our noise, all of our ripple that we had on our filter here has gone all the way through, because now we don't have adequate filtering on the output or the input to the set pin here. And what happens if we add a second RC filter in here? Once again, 10K and 100N. Bang! There's our output voltage, exactly the same scale as before, but our ripple has dropped very, very significantly. And once again, that's with no, practically no output filtering or no filtering on the set pin. And if we replace our filtering back, our 22 mic here and our big capacitance on the output, bang, there's our noise. It's suddenly vanished. These little spikes in here are going to be due to ground bounce and stuff like that. You can actually see the bounce in there. Is to do with probing and things like that, so don't worry about that. But the output noise there, look at that. Beautiful. And what happens if we adjust the duty cycle here? Well, let's give it a go, shall we? Let's drop it down to say 10%. Well, of course, silly function gen only allows us to go down to 20%, but there you go. That's the expected 1.3 volts, or 20% of that 6.6 volts, because we've got a ×2 amp in there. There you go. It works fine. And if you drop that, if you did drop that duty cycle down to 1% or 0.1%, you will find that the output voltage would follow. So There you go. That's a practical demonstration of how to replace your control pot with the PWM output or a DAC output of a microcontroller. Piece of cake. Catch you next time.